Welcome to Engineering 160A, Studio Session 1.1b, LabVIEW Basics on Data Types. Computers represent numbers in binary form, meaning all the numbers are represented by just a combination of zeros or ones. A computer cannot represent every number possible. It is bound by the number of bits used to represent the number. The more bits we use to store a number, the more memory is taken up, but the more numbers we can represent. The maximum number of independent numbers which can be represented is 2 to the n, where n is the number of bits used. The highest possible value is 1 less than this, because one of the numbers represented is 0, meaning that the highest possible number is 2 to the n minus 1. For example, if we had a 4-bit number, then we can represent 2 to the 4, or 16 total numbers. If we include 0 as one of these numbers, the range of values that we can represent go anywhere from 0 to 15. To better understand where this equation comes from, let's understand a little bit more about the binary system. Well, to do that, let's compare it to our conventional base 10 system that we are used to. If I have a 4-digit number in the base 10 number system, the first column all the way on the right is the ones column. The second column is the tens column, the 100th column, and then finally the thousandths column. And any one of these numbers I can place 0 through 9. So if I have a number like 0, 4, 6, and 3, we know that that number is 3,640. Well, one way we can look at getting this number is we just take the first digit, which was 0, and we multiply it by the column number, or the ones column. This is equal to 0. The next digit, we say, okay, that is a 4, and it is weighted by the number 10. So we multiply that by 10, and that gives us 40. The next digit, 6 times 100, or 600. And then lastly, we have a 3 times 1,000, because it's in the thousandths column, or 3,000. The total number is just the sum, or we just add all of these together, and we have 3,640. Let's now look at our binary system, which is of base 2. Again, let's look at a 4-digit number. Okay. But now in the binary system, instead of being able to put in the numbers 0 through 9, we can only put in the numbers 0 through 1. The first column is still the ones column, but now the second column, which was the tens column, is now just the twos column, or we multiplied the column previously by our base. The third column then is multiply 2 times our base of 2, which is equal to 4. And then lastly, we have 4 times our base 2, which is 8. Let me look at some random binary number. So again, I'll fill in zeros and ones. Let's look at 0, 1, 1, 0. Well, what does this number actually represent? The way we get that number is the same as what we did for our conventional base 10 system. We'll take the first digit, which was 0, and we multiply it by its column weight, which was 1. And that is equal to 0. We take the next digit, 1, and multiply that by the column weight, which is 2. That gives me a 2. The third column, we have the digit is 1, and we multiply that by its column weight, which is 4. That is equal to 4. And then lastly, we have 0 times 8, which is equal to 0. We come up with the total number by just adding all of these together, or we have the number 0 plus 2 plus 4 plus 0, or 6. So the way to represent the number 6 in binary is 0, 1, 1, 0. Now let's go back to that formula. We said the maximum number we can represent is 2 to the n. So for my 4-bit number, we had 2 to the 4, or 16 total numbers that we could represent, and the highest maximum number was 2 to the n minus 1, or 16 minus 1, 15. Well, why is this the case? Let's look at our 4-digit number, or 4-bit number. The maximum this can be is if every single digit is at its maximum value, or 1, 1, 1, 1. Okay. Well, what number is this? This is the ones column, so we have 1 times 1. This was the 2 column, or 1 times 2. This is the 4 column, or 1 times 4. And lastly, we have the 8 column, or 1 times 8. The sum, 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. So you can see that is the maximum number that can be represented by a 4-bit binary number. In LabVIEW, we can tell the computer exactly how we want the numbers to be stored. Integers are given blue symbols and can be found in 2 different types, signed and unsigned. Let's first look at an unsigned 8-bit integer given by the symbol U8. This means our number is represented by 8 bits, or we have the ability to represent 256 numbers, or a range of 0 to 255. If we use an unsigned 16-bit integer number, then we have the ability to represent 65,536 different numbers, or the range of 0 to 65,535. The difference between an unsigned integer and a signed integer is the fact that we have the ability to put a plus or a minus in front of it, or represent negative values. When we do that, we will cut the maximum number that we can represent in half, because looking at a 16-bit signed integer, with it being 16-bit, we still have the ability to represent 65,536 different numbers, but now half of those numbers are in the negative range and half are in the positive range. Therefore, now our 16-bit signed integer range goes from negative 32,768 to 32,767. One of the bits is used to denote the sign. If we don't want to represent only integers, but now have the ability to have numbers which have decimal values, then we will have to use floating point numbers. There are 3 different types of floating point numbers, and all based on the number of bits used. A single precision floating point number takes up 32 bits of storage. We can increase the maximum number of decimal point values by increasing the number of bits. We can go up to a double precision floating point number, which is 64 bits of memory. That is the default in LabVIEW. If we wanted more precision or more range, we can then use this extended precision floating point number, which utilizes 128 bits. Let's take a look at this in LabVIEW. To start, let me go into the block diagram and create some sort of numeric value. So let me go to the numeric palette and let me just create a numeric constant. So here we see that I have a blue symbol, or this is an integer value. So let me put number 1. Also, let me then create a double precision numeric constant. And let me make that a value of 5. Okay, let me hover over the terminal, right click, and I can go to create and quickly create an indicator. So here I see I have a numeric indicator. It is an integer indicator since it is blue, and here you see the designation I32, or it is a integer value, 32-bit, and it is signed. Let me hover over the terminal for my double precision number, create a indicator, and I see I have an orange indicator denoting that this is a double precision number. Let me slide these over a little bit, and let's take a look at how these things function. Let me first try and see I have this blue integer number. If I want to represent a decimal, a integer value won't work. So let's see what happens. If I put 1.5 and hit enter, I notice that what was a blue number, meaning it was integer, has now automatically changed to orange, or has become a double precision number because it had to represent a decimal value. So now we can see that we have an orange wire going into a blue or integer indicator. Well, that seems a bit strange. But if we look closely, we can see a very small red dot which has appeared. This is what we call the coercion dot. What this does is it allows the viewer to understand that LabVIEW has automatically made a formatting change. It knew that a double precision number was coming in and needed to convert that in order to be displayed as a signed 32-bit integer. If we wanted to then change my 32-bit signed integer to a double precision floating point indicator, all I need to do is right click on the indicator, go down to representation, and change it to a double precision number. Now you see that I have a double precision indicator. It is turned to orange and my red coercion dot has disappeared.